Hello, welcome to our technical session on innovation in wastewater collection and treatment. In this session, they'll have two presentations, followed by a Q&A section. My name is Wayne Williams, the Executive Director of the Caribbean Water and Wastewater Association, the CWWA. I'm pleased to moderate these two sessions today, as I think they are the way of the future. One uses more technology and one uses less, but both are effective depending on the situation. I'd like to first thank our sponsors, and we really appreciate the support that they give us in the conference. We have Sandpick Contracting Cayman, we have Deal Metering, we have Mere Water, Water Engineering and Pipeline Company, better known as WEPCO, Consolidated Water Company Limited. We have also DART Enterprises Limited, Florida Aquastore, and Agro American. Before we can you stop? Can you stop?
Sure.
Stop. Hello. Using the and also the remediation of pollution, water, and air. Dr. Han received his bachelor's in nuclear engineering from Seoul National University, Republic of Korea in '82. His Master of Science in Material Sciences from Korea Advanced Institute of Science and Technology in '84. And his doctorate in metallurgical engineering from the Colorado School of Mines in the USA, 1991. He has worked at Samsung Heavy Industries Company and EB Tech Company Limited. Dr. Han, you may now turn your microphone and webcam on. As I see your webcam is on, and you may start your presentation.
Many thanks, dear Mr. Williams, for introducing me. Dear participants of Caribbean Water and Wastewater Association Conference, greetings from Vienna. This is Mr. Bomsu Han, Radiation Chemist of IAEA. It is an honor and pleasure to present these recent activities of IAEA on wastewater treatment by radiation technology. So the International Atomic Energy Agency is the world's central intergovernmental forum for scientific and technical cooperation in the nuclear field. It works for the safe, secure, and peaceful use of nuclear science and technology, contributing to international peace, security, and the United Nations Sustainable Development Goals. The IAEA was created in 1957 in response to the deep fears and expectations generated by the discoveries and diverse uses of nuclear technology. The agency was set up for the world's Atoms for Peace organization within the United Nations family. From the beginning, it was given the mandate to work with its member states and multiple partners worldwide to promote safe, secure, and peaceful nuclear technology. The objectives of the IAEA's dual mission to promote and control the atom are well defined in the article of the IAEA statute. The total membership of IAEA is 173 nations as of April 2021. Nuclear science and technology is the foundation for all IAEA activities. The agency assists member states with the scientific advice, education, training, and technical documents in many nuclear science areas, provides key nuclear data, and helps them improve awareness about the wide range of applications of nuclear technology. The nuclear science and application of IAEA cover a broad range of socio-economic sectors, from health, food, and agriculture to the environment, water resource, and industry. It assists member states meet their development needs through nuclear science, technology, and innovation. It also works with laboratories, universities, and research facilities worldwide through the IAEA collaborating schemes. The IAEA maintains So it's hard to control, but okay, it is there. The IAEA maintains 8 nuclear application laboratories in Weibersdorf, Austria. They support and implement activities that respond to the development needs of member states in a range of subject areas, conduct applied research and development, deliver training and capacity building to member states, and provide technical and analytical services. Division of IAEA environmental laboratories comprise four separate laboratories that together constitute that IAEA's environmental laboratories in Monaco. They use nuclear and isotopic technologies to understand and propose mitigation strategies and tools for the environmental impacts of radionuclides, trace elements, and organic contaminants, as well as climate change, habitat destruction, and biodiversity loss. Pollution occurs when chemicals and other foreign substances leach into the ground, air, and water. These pollutants contain toxins that adversely impact ecosystems and the living creatures within them. Although environmental health and safety groups work to increase awareness of the dangerous pollution presence, if pollution continues at its current rate, the future effects could be harmful to human pollutions and the environment. Water pollution comes from the industry and agricultural runoff, and in addition to presenting a danger to aquatic life, water pollution also impacts humans, since the extinction of marine life adversely affects the food chain. As pollutants lives that increase, the human exposure to toxins will also increase. The Environmental Protection Agency notes that the exposure to pollutants is directly linked to cancer and heart disease. Pollution, due to its ability to cause illness in humans, can have a significant impact on the world's economy. The World Health Organization notes that an increased rate of illness due to pollution places a financial strain on many governmental systems and individuals themselves. So, it is becoming increasingly clear that the humankind's environmental problems are no longer merely local or regional, but have become continental in scope. Economically and technically feasible technologies for controlling pollution from gaseous emission and liquid effluent streams are being sought by technologists working in a variety of areas, including radiation technologists. Over the past few decades, extensive work has been carried out on utilizing radiation technology for environmental remediation. This work includes the application of radiation technology for simultaneous removal of sulfur oxide and nitrogen oxide from flue gases, purification of groundwater, treatment of wastewater, hydrogenation of sewage sludge for use in agriculture, and recycling of plastics for value-added products. Conventional wastewater and water treatment focuses on the removal of organic impurities, removal of color and odor of effluent, and removal of nitrogen and phosphorus to avoid that over-nitrification. In comparison, the radiation technology provides either removal of impurities, color, and odor, and also disinfect of microorganisms, including pathogenic organisms, and destructs residual chemicals such as persistent organic pollutants, endocrine disruptors, pesticides, and pharmaceutical residues to allow safe discharge of effluent to river or to reuse in industry or irrigation purpose. The high energy radiation produce instantaneous radiolytic transformations through energy transfer from high energy photons or accelerated electrons to optical electrons of water molecules. Absorbed energy disturbs the electronic system of the molecule, and they result in the breakage of interatomic bonds. Hydrated electrons, hydrogen atoms, OH radicals, HO radicals, hydrogen peroxide, Hydrogen molecules are the most important products of the fragmentation and primary interactions. These are the radiolysis products. Radiation processing of wastewater is non-chemical and uses fast formation of short-lived reactive radicals that can interact with a wide range of pollutants. Such reactive radicals are strong oxidizing or reducing agents that can transform the pollutants into liquid waste. For practical treatment of wastewater, radiation processing offers several advantages. They can provide the strong and reducing oxidizing agent, and universality and interchangeability of redox agent, variety of passes for pollutant conversion, process controllability, wide choice of equipment and technological regimes, compatibility with the conventional method. The first full-scale application was reported for the purification of wastewater generated at the Voronezh synthetic rubber plant in Russia. Electron beam was used to convert non-biodegradable emulsifier presented in the wastewater to biodegradable forms. The Voronezh plant has two purification lines, each equipped with an accelerator to convert non-biodegradable emulsifier presented in the plant waste to biodegradable forms. On the basis of observation following the radiation treatment, it was discovered that the product of emulsifier can be readily degradable, followed by tertiary biological treatment after irradiation. The installation treats up to 2,000 cubic meters of effluent per day. So I want to move my slides forward. Okay, now, yes, not too many. The IAEA organized several coordinated research projects on water and wastewater treatment. In late 1990s, the agency conducted irradiation treatment of water, wastewater, and sludge, and resulted in the several pilot-scale operation of wastewater and sludge plants in Korea, United States of America, India, and Argentina. The CRP on the remediation of polluted waters and wastewater by radiation processing showed the first industrial-scale wastewater treatment plant, and it is connected to another CRP on radiation treatment of wastewater for use with a particular focus on wastewater containing organic pollutants, with the dissemination of this technology to other member states. The first studies on the radiation treatment of wastewaters, principally for disinfection, were carried out in 1950s. In the 1960s, these studies were extended to the purification of water and wastewater. Laboratory research on industrial wastewaters and polluted groundwater was conducted in 1970s and 80s. And in 1990s, several pilot scale, including mobile unit facilities, were built for extended research. Extensive study has been carried out on the purification of industrial wastewater by radiation processing, although generally on the laboratory and to lesser extent the pilot scale. Convinced on the feasibility from pilot plant, an industrial plant for treating 10,000 cubic meters of textile dyeing wastewater with the electron beam has been constructed and operated continuously since 2005. This plant demonstrates a reduction of chemical reagent consumption and the reduction in retention time with the increasing in efficiency of removal of COD and BOD up to 30 or 40%. Increase in removal of efficiency after radiation treatment is due to the radiolytical transformation of non-biodegradable compounds to more readily digestible forms. Similar industrial-scale plants are also constructed in China through the IAEA Technical Cooperation Project. In 2017, A pilot facility for 1,500 cubic meters of wastewater per day from textile factory was built in Jinhua City, China. And later, in 2020, industrial plant capacity of 30,000 cubic meters per day from textile industry was also constructed in China. The IAEA also supports several different projects for wastewater treatment. The agency supports grafted membrane developed by radiation grafting technology for wastewater treatment to make technology affordable to small and medium-scale industries in order to mitigate industrial wastewater pollution. The agency also supports the on-site demonstration of radiation technology by supporting the development of mobile EV plant. For example, in Brazil, to establish a mobile unit to treat industrial effluent for reuse purpose. This will provide an effective facility between a laboratory scale to the larger scale plant with the objective to demonstrate the efficacy and transfer the technology. Attention is directed toward the radiation chemical decomposition of pollutants in groundwater and also to municipal effluent. The wide application of fertilizer, pesticide, fungicide, and other agents in recent agriculture can lead to ground pollution and consequent contamination of water resources. Research is aimed at decomposing contaminants, including chlorine-containing compounds in groundwater and polychlorinated biphenyls in transform oils by radiation, have been done by a number of research groups. The agency organized coordinated research projects on inactivation of biohazard and removal of emerging organic pollutants to exploit the innovative methodologies and technologies to remove the emerging pollutants such as endocrine disruptors, pharmaceutical residues, and other toxic pollutants in wastewater and sludge by radiation. The study suggests that the relatively low doses will be sufficient to disrupt such organic compounds. Plastics are indispensable to modern life. Plastics generate multiple benefits and conveniences, yet the vast amount of the plastics produced and eventually discarded are harming ecosystems, with grave implications for biodiversity, food safety, and ultimate human health. Approximately 70% of all plastics produced to date is now waste, and only 9% of this has been recycled. The plastic by design, durable, and this longevity means that even as waste, it does not decompose. When it reaches to the ocean, it can remain there for hundreds of years, and over time, it fragments and becomes micro and nanoplastic, which can enter the food chain more easily due to its small size. Ultimately, plastic does not disappear, but rather accumulates in the oceans over time. On the current trend, the oceans are expected to contain 1 ton of plastics for every 3 tons of fishes by 2025, and by 2050, there will be more plastic than fish. Radiation technology can be used to transform of recycled plastic waste into other products, such as fillers, binders for construction materials. They can be used to break down and convert waste plastic polymers into fewer or smaller components to generate chemical feedstock to produce consumer products. Furthermore, radiation technology offers cleaner production and recycling process, thus reducing the use of potential harmful additives and solvents, as well as delivering energy savings. The IAEA has developed new tech plastic to assist the IAEA member states in integrating nuclear and nuclear-derived techniques in their efforts to address challenges of plastic pollution, making IAEA's contribution to solving this global problem are more apparent and perceptible. New Tech Plastic builds on a portfolio of IAEA research and technical cooperation projects around plastic recycling using radiation technology, and marine monitoring of microplastics using isotopic tracing techniques. Biotech Plastics positions IAEA on an important issue of global concern, plastic pollution. Radiation technology is quite effective for remediation of contaminated environment. When irradiated with high energy radiation, practically all the energy absorbed initiate ionization and excitation to result in the formation of free radicals and these molecular spaces. So these radiolytical products can react with the harmful chemicals in the waste and convert them in the safe forms. The DIAEA helps member states strengthening their capacities in adapting radiation-based techniques that support cleaner and safe industrial processes. It also supports them in applying radiation technology for the management of industrial waste and effluent and the recycling of plastics. The IAEA statute mandates it to encourage and assist research on atomic energy for peaceful uses and its practical application. This also fosters the exchange of scientific and technical information and the exchange of scientists in the field. If you have any questions or queries, please do not hesitate to contact us. Thank you for your attention.
Thank you, Dr. Han. That presentation was very interesting. I like that you're not only removing the regular fecal coliforms, but chemical and organic pollutants as well. I like that a lot. Thank you. And now I'd like to introduce our second speaker, Mr. Alphonsus Daniel. Mr. Daniel has been a practicing mechanical, sanitary, and environmental engineer for 35 years, with a wide range of experience in planning, design, supervision, and management of water and wastewater systems. He graduated in 1986 from ISP Jam, Cuba, with a Bachelor's of Science and a Master's of Engineering in Mechanical Engineering. After graduation, his experience has been developed through working with the National Water and Sewage Authority in Grenada. And later, in 1994 to 96, he pursued a postgraduate diploma and a Master of Science degree in Sanitary Engineering from IHE Delft. He is the sole founder of Daniel & Daniel Engineering in 1999. Daniel & Daniel Engineering has been performing consulting services for various private and governmental organizations in Grenada and the wider Caribbean. He is a past president of the CWWA and past president of the Grenada Institute of Professional Engineers. He is also the current president of the Rotary Club of Grenada for the years 2021-2022. Mr. Daniel, you may now turn on your microphone and webcam and start your presentation. Thank you. Microphone.
All right. Good. You hearing me now? Everybody hearing me now, right?
Loud and clear. Thank you.
Thank you very much for that introduction, Wayne. And let me say to the audience, it's a pity we can't be in person in Cayman Islands on this 30th anniversary. But we'll be there virtually and do what we got to do. My task this morning is to present to you on some work that we are doing in St. Kitts with respect to coming up with a pilot grey water project suitable for treating of grey water and reuse at the College Street gut in St. Kitts. College Street gut, if you visit St. Kitts, you would know there is an ongoing problem in terms of the volume of wastewater that is discharged into this gut untreated and hence in the marine environment. Let me just get this right. Okay. Okay, the slides are not staying, I don't know why. Any reason why? I just wanted to go through what we want to go through. Agenda, as we said. Basically, well, the introduction was done. We'll be looking at some of the grey water management strategies. We'll be zeroing on recycling of the grey water. I want to talk briefly on centralized versus decentralized system and why we zeroing on a decentralized system. Also, we'll talk about the guidelines for WHO in terms of grey water reuse in agriculture. It would be remiss of us if we don't talk about reuse, recycle, and the green economy, circular economies. And winding down, we will talk about constructed wetlands, the treatment of wastewater. I will tell you why we ended up, the consultants, after a lot of deliberation, ended up with constructed wetlands as the main, the relevant system of a method of treatment. We'll talk some costs. And at the end, I will give you the pros and cons. I will summarize, basically, I'll do a comparative analysis of the suitability of different systems for wastewater treatment and in particular, grey water treatment. So by way of introduction, I could tell you that grey waters is called, on the other side of the Atlantic is called sewage, right? And is that water that is created or is spent water that you use after showering, bathing, or bathing, and doing your laundry. Now he gets his name from grey water because of his murky appearance. It's not as dark as sewage or grey water as we call it from the toilets, but very much it is distinguishable from tap water. And let me say from the onset, grey water contains a low amount of contaminants than black water. And therefore, we have to bear in mind upfront that it could be used in terms of reuse, several purposes in and around the home. In terms of grey water management, I like to say it, and I see it back to where I was born in the early 60s. The simplest and cheapest way to recycle your system is to capture your shower and bath water in a bucket and flush your toilet with it. Another simple way is, for example, your washing machine. Catch your washing machine, water in a tub, connect your tub to an outlet, and do irrigation of your garden. All right. Grey water can be used for other purposes like washing vehicles, driveways, mopping, and cleaning the sideways and staircases, and so on. Now, we have to bear in mind that the contaminant elements present in grey water are from soap, shampoo, toothpaste, shaving cream, and so on and so forth. And most importantly, you have some organic matter and nutrients. The nutrients I like to highlight, nitrogen and potassium, because in a view of recycling and reuse, those are two important elements that usually go down to waste when you do conventional treatment. These constituents that I mentioned don't necessarily harm the soil or plants, but we must be mindful there are some plants that are what I call highly susceptible to salts and phosphorus. So when we apply, we must be mindful and test the volume of salts and phosphorus before we put them on plants, because there are plants that will be stunted if they have too much phosphorus. Moving on, I have a schematic here, lovely schematic. And if you could get the world to do that, we'll be in a better place. Your clean water could come in on your kitchen and so on, and using your bathroom and your laundry and so on. Then you collect it, you treat it, some form. My preferred, I use the schematic of a constructed wetland, but you could do any other treatment here. Then you collect it. Then that water you use to flush your toilet, right, to clean your floors, to wash your cars, and to do your gardening. I also put up this one here that I love when I pick it up. Examples of reuse of my slide's giving some trouble. Reuse of water, not grey water alone, but wastewater worldwide. And I want to really highlight, look at Israel. Israel is treating 80% of the wastewater, and they're using sometimes nearly 100% of it is reused. Also, Singapore, we would have known and heard about the new water. Singapore treats wastewater to a level where it is bottled, because they in terms of the influx of tourists and so on, they don't have enough water to deal with the locals and also the influx of tourism. So recycling of wastewater is a big thing in Singapore. Moving on, may I touch on what I call centralized versus centralized systems? Why? I don't want to waste your time on that, but that is so key in my view to this project. And I said, based on the mandate that we were given, it begs the question, well, why the city of Bastia do not have a central sewage system? Why the same situation exists in neighboring St. John's in Antigua? Then I asked myself, home in Grenada, for example, there was a central sewage system built in the 1930s in St. George's, but up to this day, it still serves less than 5% of the population. Again, when I look at Castries, for example, they have a similar central system. For the last 30 years, they have a broken outfall that has not been repaired. Same thing could be said about St. Vincent and so on. And the short answer to this question is that centralized systems are just too expensive. And the whole traditional wastewater management concept is a centralized one. You collect all your wastewater and you send it to a central treatment plant, right? And that in itself is difficult to adopt in these poor small countries, especially, for example, St. Kitts, Bastia, as it were. So to overcome the situation, we're moving away and we concentrating on what I call a decentralized wastewater system. And we're mindful of that, right? And we're saying with the decentralized system, the solutions of treating the waste should be as close as possible to where the problem starts. You know, the way the wastewater is generated. So this is one of the philosophy, the main philosophy that we follow in designing the system, the work we did, and we are continuing to do on St. Kitts. And the decentralized system, there's a few attributes. Obviously, it must produce a good effluent quality. It must be low cost in terms of capital, installation, operation costs. And we must be mindful to use the people around the system, well train them to operate the system. We don't want strangers coming from one corner to the next to maintain the system. It must be aesthetically pleasing, and it must have a small footprint, you know, and it must, as I say, the useful life must be long. It must have a long useful life. Grey water in itself, many constituents. I like to highlight the nitrogen and the potassium. And we have to bear in mind that it has all the pollutants that the other wastewater have, but in a lesser concentration. And again, the main source of pollution in the grey water is, you know, is the chemical products. For example, the laundry detergents that we use for laundering, for having a shower, soaps and toothpaste and so on. And obviously, by the BOD and the COD are important factors which continue to indicate the strength of the wastewater, and that is important for our design. Again, these values are less than wastewater in total in general. I have, based on some studies that was done here, I have a table which we could look at in terms of what you get. Yeah, my slides are having some trouble keeping them on. I don't know why. Here, if you look at laundry, we break it down in terms of the laundry, what you get out of laundry, what you get out of the showers, and what you get out of the kitchen. Very well defined. And you know, in the kitchen would be stronger in some aspects, the laundry would be stronger in some aspects, and so on. So that is well defined. Issues of physical properties, the temperature and so on are well defined also. Obviously, grey water is would always be a little warmer because of the showers and so on that you're taking. And we have to be careful that because of the heat, you know, the temperature would favor microbial growth and so on. So that we're mindful of all of that when we are designing. Turbidity and suspended solids is very important, and it has to do with various qualities of the system. And we have to bear in mind that these could clog the system. It depends on the colloids and so on, that is, and particles that you have entrained in the system. So in terms of physical properties, we throw in color there, and suspended solids, TDS, are very high in the bathrooms, for example, you know, and mindful, the turbidity, we have that range and so on, and the temperature range. So moving on, I want to say that there are a lot of guidelines for the treatment and the use of water in agriculture. Well, reuse of, in this particular case, gray water in agriculture. Let me also say that what we found historically, the WHO guidelines were very stringent. 40, 50 years ago, the guidelines was very stringent in terms of what they asked for to apply on plants. At the end of the day, though, I could tell you that what is accepted, because they had to review it, and the concept that was using in terms of reusing irrigation, it just couldn't apply across to the poor developing countries. So I have a table here which is important, and that was guided by, and it's divided in restricted use and unrestricted use. Obviously, restricted use for irrigation of trees and fodder and so on. For example, if you look, you see the fecal coliform is not relevant there. Yes, intestinal nematodes, less than or equal to 1 per every liter is important. When it comes to unrestricted use, where you have edible crops, the both are valuable. The less than 1 nematode egg per liter, and also they stipulate less than or equal to 1,000 fecal coliform colonies for every 100 milliliter. So we follow these WHO guidelines rather than the stringent ones of US EPA and FAO when it comes to our developing countries. Quickly, the whole concept of recycling, the green economy and the circular economy, as it was. Now, I want to mention the household-centered sanitation approach that was developed by the WSSCC in 1999. And among other things, it specified that solutions for any urban environmental sanitation system should take place as close as possible to the place where it occurs. And waste, whether solid or liquid, should be regarded as a resource. And the UESS system we're talking about should be circular. It should be designed in such a way as to minimize inputs and reduce outputs. So hence, the household-centered urban sanitation system will be a household-centered planning approach. Everything will come from consultations of the stakeholders, basically mostly in the households, and they would offer solutions to solving the problem. And as we say, we want to solve this problem as close as possible to the source where this wastewater is generated. And the circular economy now, the concept is to reduce. Is not, again, it's away from the traditional linear where you just use, you know, you reproduce, you use, and at the end up you dump, and you end up in the landfill. Here we're talking about circular, where we're trying to minimize as best as possible the inputs, and we want to get out of it nutrients that could be recyclable, and at the end of the day, maximize and have a nice, happy circle where the environment at the end of the day will be better off. So the consultants are bearing that in mind in pursuing the job also. So moving on, I am jumping quickly to what I call the system of constructed wetlands, and why it doesn't mean that we do. Remember, the topic is optioneering. It doesn't mean that we didn't look at all the different options that is possible. I must tell you that we view the traditional unit operation system for treatment of wastewater, as you know, the sedimentation and the settling, the filtration, and so on and so forth. We also be mindful of the sizing and the question of the limited available land that is around the houses, that where the gray water is generated near the College Street gut in Bastia. I want to tell you that the business of constructed wetland system and treatment of gray water, in wastewater in general, started in Germany in the 50s. Is not new technology. It's technology that is tested and proven. The Danish did some serious studies in the 60s, and with them, they also mimic what we call the natural wetland system. They added the reeds, the Pragmatis australis, which we call the common reed, and Tipa latifolia, the bulrush and systems, which, based on the results, they had positive, very positive results in terms of the effluent quality coming out of these wastewater systems. To summarize, well, I must tell you, they referred to them early as reed beds, and they reported early o'clock. You're talking BOD in terms of removal ratios of BOD and total dissolved solids in the 80s to 95%. Moving on. No, I'm stuck. All right. Let me say that in Grenada, since 2006, we've been experimenting, and we have three full-blown systems working. And in our case, we planted what I call ornamental flowering plants, heliconias, ginger lilies, ornamental bananas, buds of paradise, and they bring excellent effluent quality. Based on the literature, it was pointed out, and we discovered that vertical flow systems, if well designed, can achieve an effluent level that will meet most stringent classes: 95% removal of BOD, 90% removal of total phosphorus, and 90% nitrification. And also, we got reports from work that was done in Europe and so on, that based on the effluent quality, an area of 2 to 2.5 cubic meters is needed per population equivalent of those systems, and that's wastewater in general. So it's even smaller for just gray water. I have an example here of one of the systems, the last systems, one of the second system actually that we built in Grenada, and it's blooming right now for a 3-bedroom house. You can see it here. And if you look carefully, you would see that, as I said, we use a lot of heliconias and ginger lilies to assist in the treatment process. So moving on, 3-bedroom house here, beautifully displayed on the lawn and so on, and it's working. Let me say though that I want to talk about the ornamental flowering plants. And I found Sandoval and these guys, a group of engineers based in Mexico and so on, did some wonderful work. And apart from just the reeds that was used early o'clock, they decide to use ornamental plants and see what they get of it. In the study that they found out that 4 ornamental plants made sense: the Cana lilies, I have them growing close to the office, the iris, the heliconias, and so on, offered even more better removal ratios on the wetland systems when they are used. Before we go into cost, let me just run that over. Somehow the slide's giving a little trouble, but we'll get there. Right. Again, a lot of work was done. S. Gorky did some work, and she found out that these systems would give, in terms of TSS, total dissolved solids, total suspended BOD and COD, you're talking 60, 66, 89, 85, and 82%. In terms of the use, in terms of costs, we found out the cost could vary dramatically across the divide. In terms of well, first of all, you start with the type of system you want to do. And this goodly gentleman here in 2008 summarized nicely. And we talk about horizontal flow systems, which is most prevalent. And they look at what was done in the US, in Czechoslovakia, Portugal, Spain, and so on. And they found out that the excavation cost varied between 7 and 27.4% of the total capital cost. When it comes to the gravel that was put as a media into the system, they get a variation of 27% to 53%. If you have a liner, you're talking 13 to 33%. And in terms of the plants that you choose as the emerging species, 2% to 12%. Plumbing, 6% to 12%. And then the control structure is 1.3 to 5%. Now, the total investment cost may vary also. And what in our studies, we realized that if you start from India, you're talking about $29 per cubic meter. And that was information from 1999, $33 per cubic meter in Costa Rica, and so on. And it could be as high as 257 euros per cubic meter in Belgium. Our experience in Grenada, this system's constructed, for example, what I call a 3-bedroom house. You need $4,780. It works out then to be $357 per cubic meter. And the media that we used were 3/4 minus crushed stones from the quarry. And also we planted ornamental flowering plants, heliconias, ginger lilies, some of the canna lilies, and so on. So winding down, constructed wetlands have low operation costs, operation and maintenance costs. You must be mindful. Yes, we have to do some vegetation harvesting when it's necessary. Basic costs are much lower than those of the concrete and steel technologies. And we're talking about it's cheaper by a factor between 2 to 10, depending on which side of the world you are. In addition, because wetlands have a higher rate of biological activity than most ecosystems, they can transform many of the common pollutants that occur in conventional wastewaters into harmless byproducts or essential nutrients that can be used for additional biological treatment. Oh boy. Okay. After this course here, we did a summary. We did a summary, which I could go into now. And you know, for details, you'll follow the paper. It's there. What we did a comparison with traditional septic tank and filtration system, typical package systems, because we look a lot at the package systems that they offer. A lot of MBR systems with filtration. Yes, they are compact, but you know, when we start looking towards it as a solution, we ask ourselves, hey, these could really work. You know, you could get individual households to purchase those systems and maintain them because they are energy intensive. Some of them are blowers. You know, you have to push through membranes. You're talking electricity costs. Electricity costs is not cheap at all in the Caribbean where we use fossil fluids. So we did that. We weighed against waste stabilization ponds, and we also weighed against settling tank and constructed wetland, which is what we ended up with, and so on. And we did general conditions and so on, which we were able to compare. Is it appropriate? Yes. And innovative, and so on. And we break that down. Waste stabilization ponds, obviously, it wasn't applicable to too much land. Treatment efficiencies, we look at it. Septic tank versus settling tanks, for example, moderate versus the treatment system is excellent. In terms of social acceptance, in the countries where they are constructed, yes. And we did a whole host, as I say, when it comes to the land, which is very crucial in the decision making. You know, when you look at septic tanks, for example, you're talking about 23 square meters per 5 PE, you know. versus in the wetland system only need 5 square meters of land to construct a system that will treat a household, for example, of 5 persons. We also look at financial, we look at public health, in terms of recycling, environmental, the possibility of recycling. Yes, you have it in the 3 of them, and then so on. The energy use. Look at the settling, the constructed wetlands, almost nil in some cases if it's gravity flow, and so on. In terms of reuse and sludge and all that was looked at. Eutrophication potential of the effluent, very low for constructed wetlands, and so on. In terms of public health and so on, we were able to assess the issue of all the systems, also the acceptance again, and we found out, for example, potential for reuse. The settling tank and constructed wetland, excellent quality for reuse and irrigation. And also the capital costs. We had the capital and the O&M costs. We could look at the summary here to compare it against, for example, the mechanical systems at $13,600 US in terms of capital for PE to treat a household waste from a household of 5 persons. You're talking 13,600 versus that of the constructed wetland, 3,900. And the expected life, the life expectancy of these systems is between 50 to 80 years. Again, we can't stress operation and maintenance, very low, very minimal, and so on. So this is where we are, and we have the last slide, which doesn't want to come up, but for some hitch, it's going to come. Okay, so concluding, in viewing everything, one of the things that stuck out is that there's not enough land space to accommodate systems. Some of the systems I mentioned, the land space is a critical factor. We also view that for the system to survive, the necessary skills to operate them must come from among the households. This was paramount in our minds, right? And we remembered in all the commercial systems that we looked, the package plants and so on, they all were energy intensive, but a lot of moving parts. So that rendered them not sustainable for this project. The commercial systems are also not nature-based, and the mandate we got in the terms of reference, we should try the system that we settled on should be nature-based, yeah, and they should be considered as sustainable. Okay, and then we did a comprehensive study consultation with all and sundry in and around the gut that are affected, and they all agreed that wastewater going down the gut is a nuisance, it impacts the environment negatively, public health, life, vehicular traffic, and so on. And they would support, and likewise the government officials, that something should be done to alleviate these problems. So we have a design here, which it's theoretical. It was based on the organic loading, but we came up finally with a system. One of this was, you're looking at here, would treat a household of 5. But for the pilot project, we decided to design 3, so we could compare the results. Here we did a vertical, we did a horizontal, and we did a third one, which is horizontal, where we could add, maybe not put plants. These would have plants, and we could compare with results that we will get when we have ornamental flooring plants and when we don't have. So that's what it is. We just costed the system, and we're looking at 75,000 EC dollars to construct that pilot plant. So this is what I wanted to share with you. Remember, my mandate was nature-based, keep it simple. We apply the KISS the KISS principle, keep it simple and sustainable. I thank you very much. Any questions?
Thank you, Mr. Daniel, for your presentation. At this time, everybody in the session may participate in Q&A. I'm going to ask Dr. Han to turn on his camera as well and his microphone just as we start. Please keep your mic muted until called upon. If you have a question, just as if you were in person, you may raise your hand and I'll call on you when it's your turn. You can also submit questions in the chat. We have some questions already in our chat via text. If you don't have a microphone or camera available, we'll do all our best to answer our questions. If we do run out of time, you can find Dr. Han and Mr. Daniel's contact information on the speakers page in Hova. So let's start with the question. The first question, Dr. Han. The first question was to you, Dr. Han, and somebody asked about, can you talk a bit about the energy consumption of electron beam radiation in wastewater treatment compared to more traditional methods?
Thank you very much. Those nice questions that the people believe that the electron accelerator may consume a huge amount of electricity, but however, the energy required to treat wastewater is 1 kilogray. That means that 1 kilowatt for 1 kilogram of water is used. So that the cost of 1 kilowatt hour of electricity is usually 15 cents, the euro cent or the dollar as the cent. So far, the treatment cost of electricity is quite low. And compared to the conventional treatment, for example, in textile dyeing wastewater plant, the user and conventional treatment cost is around $1.2 per cubic meters, but electron beam processing is 80 cents per cubic meter. So, of course, it is more economic for the larger scale plant. For the small treatment, the cost, the capital cost of a facility is quite high, but some thousands or 10,000s of wastewater per day of facility, the electron beam process has technical and economical advantages. Thank you.
Right, thank you for that. And just as an extension of that question, you mentioned just in the end the capital costs. Could you say a little bit more on the capital versus life cycle costs?
Yes, for example, treating 10,000 cubic meter wastewater plant, that the capital cost for even facility is in total around $3 million US. That including the accelerator, concrete shield, technical lines, and water, pumping, and all others. So far, by introducing electron beam technology, we can reduce the consumption of chemicals for chemical treatment and also improve the retention time in biological treatment. So we calculated after the operation of plant in 5 or 6 years, the capital cost investment was returned within 3 years by saving the cost of chemicals and other logistics.
Great, thank you. That's pretty good. To Mr. Daniel, who would operate, other than the ones obviously that are on people's own property, but who would the public ones, who would operate the decentralized plants, the community or the utilities?
Well, I to be honest with you, based on the situation, we should find common ground. Obviously, I would advocate when it comes to what I call communal, which may take in more than, let's say, a village, 2 villages close by. It will always be wise to train a cadre of persons who would be under the supervision of the water department or the environmental department. It's kind of unique. The water department is not really in charge of sewage yet, so that may fall under the purview of the Department of the Environment. But a trained cadre is important, and they would cross what I call cross-fertilize their experience and so on with and help check on the householders who are maintaining those that are private on their property. At the end of the day, based on my experience, what I'm seeing with the households in Grenada, the householders would have a lot to teach would have a lot to teach the cadre of people that coming from the government side. You know, they have it right in the backyard, and they know what it is. In the moonlight, they look at the flowers. I was talking to the gentleman, and he says, you know, because of this lovely system, actually came from England, COVID came, and part of his pastime is looking and trimming and making sure everything, especially in the moonlight, looking at the birds of paradise and the heliconias. So they would have a story to tell in terms of the care, you know, and so on for its survival, which I think would be superb and over what the cadre of what I call operators and the government will have. Yeah.
Thanks. All right. Follow-up question. How are oil and grease shocks? How do they affect constructed wetlands, and how do you deal with them?
Based on all the studies that we review, and well, what I've seen even in Belgium and Netherlands when I was in the Netherlands when I was doing my training there, two things. We're looking at domestic, first of all. The volume of grease coming from the houses could be handled easily by the systems we're proposing. Now, I want to say, though, in my view, if the houses start being apartments, and you know we operate in the Caribbean, in one of those apartments, somebody decided to start a shack and bake. I see Wade shaking his head, a shack and bake shop where they're frying 24/7. We'll advocate that it conveyed, that wastewater from that specific kitchen be conveyed to a grease trap first, right? It will make a lot of sense. Notwithstanding that point though, bear in mind that the system that we are advocating and we have designed as a pilot, and we hope would proliferate as the years go by on the what I call the houses near the gut. We have a small settling tank upstream the wetland system. So with that settling tank, you will get some handling of the grease. The grease, a lot of the grease, whatever escape, right, through the kitchens. If festivals come and you're using more grease in the household, a lot of it would settle in, well, not settle, but float and be form part of the supernatant in the settling tank. And that could be skimmed off. The rest, anything that escape and entrain, the wetland system handles it properly and easily. Yep.
Thanks. So the basic design, let's say for the system at the house, yeah, that lovely pictures you had there with the 3-bedroom house, etc., with the plants in the middle, has a septic tank before the wetlands.
Correct.
And it is a gray water tank?
Well, the one I'm showing there, the one I'm showing specifically there in Grenada, that was for everything. It's a mixture of the gray water and the black water.
Great. And then after the constructed wetlands, does it go anywhere, or?
Yeah, we have in that case here in Grenada, we have it going to a chlorine contact chamber as an option if you want to. And as I told him, he said, yeah, well, it's one of it was constructed in a dry part of the island. So come dry season, we also constructed an optional, what I call optional holding tank for irrigation for him. So on as a composite with that, we have the possibility of chlorination. So you could chlorinate, put in a pump, and irrigate the lawn if he wants also. And after that, though, it goes into a leach field or a drain field, which eventually drains and clean water, if it escapes at all to the adjoining drains, it's clean water ready to bottle just as new water in Singapore.
Okay, all right. Let me switch to Dr. Han. Question, I also had this one when I was looking at that, understanding the public perception that we may have to overcome. How can you talk a little bit about the challenges faced in implementing the radiation wastewater treatment?
Yes, the public acceptance was not easy for all the application of radiation technologies. Like some countries still hesitate to applying the food irradiation, but you can find that in many industries, or especially for the polymer industries, to make a cable, wires, and tires, there are close to 20,000 electron accelerators are used in industry. And so, in most cases, for polymer and other industry, it is acceptable. But for that environmental applications, we already built several plants for wastewater treatment in Korea, China, and other places, and also for the gas treatment in Japan, Poland, China, as well as treatment in Germany and India. So people are always aware about that something when irradiated with some water, if something like some new species are generated and whatever. But the irradiation used in this technique is not that high to make any mutation or any changes in irradiated places. So, and also we checked that all the toxicity indexes after the irradiation from the wastewater, if there are any chances to produce the new toxic compounds or not. But there was no any harmful effect on the wastewater. And then when the radiation interacts with the water, they dissociate and ionize the water molecules in very short times, and then unreacted radicals recombine to water molecules. So no any further radioactivity is remaining, no any harmful, but still need to make more training and education and advertisement of technologies for about the public acceptances.
Yeah, and I noticed that some of the byproducts was the hydroxide and even peroxide was one of the byproducts, highly oxidative. I love that about the system is that it not only deals with the fecal coliforms that is traditionally in wastewater, but it also, because of the high oxidative nature, that it attacks other items. That's one of the things I liked about the ozone, in that it goes after other things that you're not necessarily treating when you do traditional treatment. Yeah.
Yes, right. It is kind of advanced oxidation processes, but not like the ozone and other things that we don't need. We don't use any other chemicals, and also ozone is difficult to dissolve in the water, and also the ozone need for stripping and others. To after treating, the ozone also needs to special cares. But with this radiolysis, we made radicals, and if the radicals are not used, they recombine to the water molecules. So we make everything from the water and back to water.
Yeah, basically the hydrogens and the
Yeah.
oxygens. Yeah, very good. And a system like this, how long? I mean, obviously, there are really no moving parts. So how long will the system last before having to be?
Yes, because that basically the accelerator has no rotating part, so the machine can stand over 20 years. But you need that the pumping of water and others, they can replace with other components periodically. But except that, nothing for special cares, for no chemicals, no short period of components and others. So it is quite stable and only need the electricity to operate the machines. And you can switch on, switch off the systems and can be fully automatic. And so, yeah.
One of the statements or comments that was made is considering rebranding radiation wastewater treatment to electron treatment to help with the public
Yes,
perception.
right. So we do not use the technology radiation. We say that electron beam treatment or high energy treatment, ionization, and so on. So because that people has very perceptions about that the radiations and damages and so far, but it is quite a peaceful use of another side of the atomic energies.
Yeah, and we're forgetting that we may forget that we're trying to kill microorganisms. So you really don't need a lot to do so. I mean, in fact, with COVID, they say wash your hands with soap and water to get the virus. So you don't need a lot to do what you're doing. Yeah, definitely so. Alfonso, a question for you. What would you recommend as the smallest population coverage for nature-based system outside of an individual system? I guess it would be to replace perhaps a package plant. You did mention apartments. Those are the in-between sizes usually that are where you start looking for apartments, health centers, police stations, small hospitals. Yeah, those. Yep.
Well,
health centers.
Yeah, because obviously, if you go outside the 3-bedroom apartment, we're talking about a household of 5 and so on. We have to scale up, and scale up is not a problem. That's why we're using PE, population equivalent. So you calculate and you size to suit. And what I've seen in the literature, we have 3-4 different approaches. The one which we took is what we could calculate basically is based on flow, the hydraulic loading. But you could some designers do one and compare it with the other and get the amount of land that is in terms of what the calculators is higher. But if you're talking 33 square feet for a household of land, for a household of 5, you could just think about what, for example, a health center would do. I mean, once you have land, as I say, you can scale up, and you're scaling up based on the volumes. And obviously the money. But I did a comparison for you in the table behind with those systems. And in all islands, we have to be mindful of the issue of the electricity. This fossil fuel that we burn is not cheap at all. As a matter of fact, I don't remember exactly what's in Kitts. For us in Grenada, we were ranking as the second highest electricity in the Caribbean after Martinique, I think. So we hope that will change with renewables. And a lot of studies show too that the systems could be powered if you ever, for example, the vertical ones, if you have an issue, for example, if you go into the health center and so on, then you might have sloping land and so on, which will work for you. You might have very flat land. You may want to just lift the wastewater with a very small pump. I'm saying small because I want to keep it small because we want to keep the energy down. And then solar. You have the solar pumps are becoming efficient these days, so in terms of scaling up, as I say, outside of just a normal home, it's not a insurmountable task.
Great.
That answers.
Mm-hmm. Yeah, and just as you mentioned, solar powered pumps, one of our exhibitors represents a solar power line right now, so I would recommend folks to check out that exhibition in Hoover. And there was a question, as you mentioned, vertical flow. There was a question on, did you have to do any vector control for vertical flow?
No. Let me be specific here. When the person asking the question in terms of vector control may be confusing a little vertical flow with what we call free surface flowing, which is where they started. The free surface is when you look at the wetland, you see like a pond. Now, what we are advocating is subsurface. Everything is under. So you look, what you will see is the flowers, the trees, plants, and the median and the gravel. So all that, and we're mindful of this miserable, harmful vectors, mosquitoes, and so on. So what we're advocating is a system that will be flowing under 6 inches to 8 inches to a foot of gravel and mulch for the plants. So in other words, no space for mosquito laying and all of that. But the issue with the vertical and the horizontal, the vertical goes up, comes in on top and spread out and then goes down. Whereas the horizontal come across and goes like that and is collected in the end. So that's the difference. But they all are subsurface, so it's under.
Okay, great, thank you. There was another question. It was very interesting to see that some of the indigenous plants could be used instead of some of the traditional reed beds and all that.
Oh yeah. I tell you, Sandoval and these guys, as a matter of fact, I made a contact with one of the guys who work with him in Mexico in the academia there. I mean, they studied in 15 countries. They went around and looked at what 15 countries doing it, and hundreds of systems. And they said, hey, if you're getting historically, we're getting so much good results from what is the common reed beds and bulrushes and cattails and the states and so on. Let's see what we have. Let's bring it back home. And they started and they did these pilots, and even better removal ratios, up to the 95, some places 96, and so on. And not only that, we have to bear in mind too that we're advocating the ornamental flooring plants, because look at the aesthetics and the commercial value. Because there you could be harvesting, your ginger lilies and your so on, and your buds of paradise, heliconias, making bouquets, and even drying the dry flower industry and so on. Big business. And we think that in terms of that, if you push that, the householders will catch on that, because it will make commercial sense to them in the long run. Yeah.
And for the systems that want to reuse the treated water for flushing, etc., they would have a separate tank and a pump, and of course separate lines to maybe the toilet tanks, etc.
Yep. And you're collecting that after the wetland. After the wetland, you have a reasonable, as I say, clean water. And if you want to go forward, I mean, we will advocate on the gardening, we're not advocating disinfection at all. But maybe if you want to scrub the floor, use it, in that same holding tank for irrigation, you could put a little composite chlorinator. The same chlorine tablets that they use for the swimming pools, the 3-inch tablets that they use. You'll drop that inside there, no hassle. The homeowners could handle that. And then you have you treated effluent disinfected, and you could roll it back out with a small pump. You don't have to be energy, and it's optional. You don't have to be used all the time for washing, flushing, and even washing the vehicles,
Yeah. Okay, great. Yeah. And there are a lot of advances with some of this technology now that makes it very simple and inexpensive. And as you say, the solar pumps, no use of regular electricity, commercial electricity. Dr. Han, there was in your presentation, one of the questions that I had until I saw it mentioned that you could treat as low as 1 meter cube per hour. I saw that you had mobile units. Speak a little bit about what those mobile units would be used for. Why would they have them? What would they be treating? Is it primarily industrial that you would put it there? Why would you have a mobile unit?
Yeah, that the mobile unit is for the demonstrations on site, because that the electron beam facilities is the big and housed in the concrete shield. So we can move the facility on site. In other hand, then we should move the waters samples to the facilities, but that was quite limited. So we built small size electron beam facilities on the trailer, self-shielded trailer, and moved to the on-site, park the trailer, and treat the wastewater some months to demonstrate the technology is working. So far however, that the cost for treatment with the mobile E-beam is higher than the stationary plant, because that the E-beam and the shielding is E-beam is quite low energy, and then the shielding, and then others all are limited. So it has built for the demonstration on site. So we have demonstrated in many places for textile industries and municipal effluent and chemical industries. And there was the mobile unit in United States, in Korea, and also recently there was the new mobile E-beam plant in Brazil, also for the demonstration. So once the technology is proven through that pilot scale plant for some months through this mobile unit, then they will design that to the stationary plant to adapt these technologies. So this is for that kind of pilot plant, demonstrate on site, in between from the laboratory to commercial scale plant.
Okay, yes, because each waste is different. So everybody will want to make sure that the outcome is the desired outcome. Okay, I can see that. Last question. Well, I think this may be the last question here from Mr. Daniel. Any plans to use the system in the agricultural sector? You had hinted on some commercial uses of it.
Well, I am
food security, etc.
I show my my mentor and the person in charge of the project. She is on Dr. Hala Saheli, and these systems that we are advocating, you find even more relevance in the agriculture sector for houses that are, where you have, like farmers and people farming and so on. I mean, that specific project is along the gut in the center of Basse there. I mean, is what half of it is what we call, what the Rastas like to call concrete jungle. But in terms of application, very much applicable, and we'll advocate it. And I'm saying so on another project, that there is no reason why you should be trying to push a central system in the peri-urban and the rural areas. These waste generated should be treated and recycled back into the land, right? So it's even more relevant when it comes to, as I say, peri-urban areas outside and the rural areas, and specifically to with respect to agriculture. Yeah.
Yep. Great. We're right at this point. We don't have any more questions, so I just want to put out there that if anybody has any questions, post them now, and so that we can ask the two gentlemen. But this time, I think it'll be fine. That I think we had a great session. I think there's a lot of interest. I know that both of them are extremely interesting to me. As you know, Alphonsus is a wastewater guy. So let's just close it off, because we do have our closing ceremony that'll be starting in about an hour. So the session has come to an end. I hope you guys enjoyed it. I know I certainly did, and I will go back and look at some of those slides to get the information. Remember, if you have additional questions for Dr. Han or Mr. Daniel, you can reach out to them by phone or email, and you can find this information on the Hoover app. So finally, I'd like to encourage you once again to visit our virtual exhibition booths to learn more what they can offer and how they can help you. As I mentioned, one of the suppliers is actually has solar pumps. So on behalf of CWWA and the Water Authority in Cayman, we are glad that you joined us, and thank you for attending.
Thank you.